Okay, let's get started. Okay, first of all, we would like to review what we learned last week. So last week we discussed the modulation, and the simple idea of a modulation is to deliver your message using your carrier. Okay, we have a message signal, we have a carrier signal, right? And how to put your message into the carrier, that's the modulation. You can put your message into an amplitude of the carrier, that's amplitude modulation. Or if you want, you can put your message into the frequency part of your carrier. That's going to be a frequency modulation, right? Which we will talk about later. So in the amplitude modulation, we have these four different things. And right now we are talking about this basic amplitude modulation, right? And here's the idea. We have a message, our own message. This is what you want to transmit. In order to transmit this message, what you want to do is you want to multiply a gain in order to make it small or large if necessary, and then you are adding a DC in order to lift this up so that all the signals is always positive. And now after that, you are multiplying the carrier. Typically, carrier is very high frequency, right? So once you multiply this with this, now you're going to get this signal. And that's ST, and that's what is transmitting over the air. Okay? So when you look at this, right, this is basically the carrier, our carrier. So mathematically, this is the carrier, and the mathematics of that is this one. Okay? This is AC times cosine 2 pi FCT. That's this one. Now, when you put the message into the carrier, we are putting the message into the amplitude part of the carrier. So carrier has the amplitude part and also the frequency part. And this frequency part of the carrier is still same, right? So this is ST, this one, right? This is ST. And we are not touching anything here. What we do is that we are putting the message into the amplitude part, like this way. And what is special in this particular amplitude modulation is that you are not just putting the MT here, you are multiplying the Ka, and also you are adding +1. That's the only difference, but still the message goes into the amplitude part of your carrier. So that's why we call this one as amplitude modulation. Okay, this slide shows you what happens if you don't do DC addition, right? If you don't +1, don't do the DC addition, now the some part of the your message still is negative. In that case, you see the phase reversal. Once you get the phase reversal, now you cannot use the envelope detector, right? Because envelope detector will only detect this one, the positive envelope. So this is not our message, right? Our message in this case goes to negative, and this envelope detector cannot detect that. That's why in order to use, if you want to use the envelope detector, you need to use DC addition. That way, all the signals is always positive, right? This is the mathematics behind that. Okay, so this is the signal that we just looked at. We have a carrier, and this is the amplitude part of the carrier. We put the message here. Since we add the DC here, you see that these are two terms, right? The first term is a pure carrier, since this is just cosine, and the second part is message multiplied by carrier. Okay, so we have two different terms in time domain. When you take a look at this in frequency domain, this pure carrier part now becomes 2 direct delta, and this part, this is we call actually as a modulation because message multiplied by cosine, and this term in time domain becomes these two terms in frequency domain. So now in the frequency domain, we have 4 different terms. And these two will be the direct delta function, which is in here, arrow here, one big arrow here. Those two big direct delta, those are this one, pure carrier term. And now, in addition to that, we have these different terms, and these two will be some triangle here, because we assumed that our original message in frequency response is this kind of the triangle. So we actually have the same thing. The only difference is that, see here, this one is M0. Right here, right? And now here you see the half of that because your energy now is split it into the half. But anyway, the important thing is that based on your message signal, your message can be anything, right? You can make your own message in any different shape. So depending on that, if you take a Fourier transform of your own message, you get your own frequency response. This is just an example. Okay? Maybe your own frequency response maybe looks like a rectangular, if you like. It doesn't matter, right? So whatever shape, whatever frequency response you have for your message, now this one will be split into positive and negative this way. And the center frequency here now becomes the carrier frequency, Fc. So now we have here. In addition to that, we have two different direct delta function, which is pure carrier terms. Okay, so this is the frequency domain response of ST. So we are talking about this one, ST, right? What is ST? This is the signal we are transmitting over the air. Okay, this is what is really flying over the air. And if you look at the ST, the signal flying over the air from the frequency response, frequency domain, this is what it looks like. This is the frequency response of ST. Now the problem of this signal is that when you compare the energy in this direct delta and the energy in your original the triangular term, now this energy in this direct delta is much, much higher than the energy in this bandwidth. And you see that this direct delta, these two direct delta, right? These are this one, right? And these direct delta originally come from this one. And this is originally from DC addition. So this is just purely waste. You are not delivering any information using this carrier. Your information is right here. Here, actually. These are your information. This term or this term has no information for your. But we need this DC. Why? Because we want to use envelope detector in the receiver. And what's the benefit of using envelope detector at the receiver? Simplicity. Okay? It's going to be a very simple receiver at the simple receiver design. Only because of that, we are adding DC. And once you add the DC, now we have this carrier term. And because of that, we have two direct delta. So you are wasting a lot of energy because of that. Okay? But that's what happened. In order to investigate a little bit more detail, what we see is that we want to look at a special message. And this is just the example. Okay, suppose that your message is just sinusoidal signal like this. So this is your message, just an example. Okay, so your message looks like this. And since this is a sinusoidal signal, you have your sinusoidal signal has amplitude, and also you have your own frequency. But this is a message. When you look at here, we still have the same ST. Originally, in the previous slide, this one was MT. Now our message looks like this, so we just replace it with this one. And in here, this is your message amplitude. This is a gain. So when you multiply these two, we're going to replace this as a mu, and we're going to call mu as a modulation factor or percentage modulation. What that basically means is this mu is multiplied into your message. This is your message, right? This is your message. So mu is actually the gain of your message. And 1 is still DC. So if you have high mu, large value mu, that means your message has a more energy. Or put it another way, if you put this mu small value, that means, because this is just constant 1, so compared to this, if mu is a small value, then your message becomes smaller. Okay? Or energy in your message will be smaller. So that's the modulation factor. So in order to look at the effect of this mu, or the value, impact of the value, what we want to look at is, we want to look at this figure. So when you look at this figure, this x-axis shows you the percentage modulation or modulation factor. So when the modulation factor mu equal to 0, then you have no information on your sideband. 100% of the energy goes to carrier, right? Because go back to here, if a mu equal to 0, then your message going to be completely 0. You have only carrier. So your carrier will have 100% of the energy, right? Now, if you increase the mu and eventually become 1, then side lobe has some power, some energy, but still the carrier energy has a much larger, right? So, but that's the case when you call the 100% modulation. This is the point where you call the 100% modulation. And right here, somewhere here is a mu equal to less than 1. So if the mu is less than 1, then we call that as under modulation. Okay? If the mu is larger than 1, for example 2, then it's called over modulation. So now let's say, if you have under modulation, then what is good? There's a good thing and bad things, right? There's always pros and cons. In under modulation, what is a good thing? In under modulation, it looks like this. So good thing is that your signal is always positive, way over positive. So it's very easy to use envelope detector. So your receiver will be very simple. So that's a good thing. What is really bad? Too much waste in your carrier. Your sideband, this is actually sideband. This sideband contains your information, but you have so little energy on this sideband. Maybe like only 1% or less than 10%. Most of the 90% of your energy is completely wasted by this carrier. So that's very bad. So the second case is 100% modulation, but let's move on to the over modulation. This is a case of over modulation, which is the mu equal to 2. When mu equal to 2, good thing is that somehow you can increase your energy on your sideband. So the energy you wasted by the carrier is a little bit reduced, right? The power in the carrier is reduced, and energy in your sideband is increased. That's good, because we are wasting less amount of power. But look at here, when you do the over modulation, now you start to have a negative in your time domain. Once you have a negative part in your time domain, you cannot use envelope detector. So in this case, you cannot use envelope detector. Okay? So that's a little bit bad, because in this case, you cannot make your receiver simple. Envelope detector means simple receiver. Okay? In this case, you cannot use envelope detector. So you cannot use a simple design. That's the problem. Okay? So that's what you want to remember. So we discussed a little bit about envelope detector. What this envelope detector is that you are simply detecting the envelope. Signal actually fluctuates because you multiply the carrier. Carrier is a very fast sinusoidal signal, but you don't worry about the carrier. What you want to do is you just detect the envelope. So for example, like this, right? This is actually ST in this example. Okay, your ST is multiplied by carrier. Carrier is very fast sinusoidal signal. But what you want to detect is this one, because this is called the envelope, right? This envelope is your original message. Okay. How to do that is that you design this kind of circuit, which we call as envelope detector. This is envelope detector. In this case, we have two different time constant. This is RC circuit. Here R, here C, RC circuit. And there's another RC circuit here. We have another R. So this RC circuit, which is this one, that RC circuit will decide what is going to be the charging time constant, because this is where you charge, right? this signal comes in here. See AM wave? This AM wave comes in here, right? So this AM wave goes up, then here has a high voltage. Initially you have 0. So since this is a high voltage, the current goes this way because we have a the higher voltage here. So the current goes down here, then it'll be charged. So when your signal goes up and positive, now this is charged. And when this signal goes down, because this is sinusoidal, it sometimes goes down, right? When it goes down, now this is charged enough. It's enough charged. Now this is gonna be some high value than this one because this one now goes down. So sometimes this one becomes a higher voltage than this one. Now then it's discharged. So here is a charging, this is the discharging. So it's like charging, discharging, charging, discharging, something like that, right? So here's a charging, discharging, charging, discharging. That's what's going to happen here, okay? So when you charge based on this RC, what you want to do is you want to charge it fast. Here, discharging, you want to discharge it slow, very slow. So therefore, you need to design this RC circuit based on these things. This one decides your charging time constant, and this one decides your discharging time constant. So if you design this RS, here's RS, this is RS, this is RL, okay? So if you design this RS, this one, and this RL, this one, carefully, okay? If you design this RSC, RLC carefully, then you can design it like charging it fast, discharging it slowly. Then what happens is this one goes up, then while this is going up, this is charging very fast. And when this goes down, now you are discharging slowly. So you are discharging slowly and then come back to charging, discharging, come back charging, discharging, something like that, right? Yeah. So that's what happened. So when you look at the charging, discharging slow, charging fast, discharging slow, then eventually at the output, you're going to get this kind of signal. Okay? And this one, when you look at it, this one looks like almost similar to envelope. Only difference is that this is not very clean, right? Because there's a charging and there's a little bit discharging, charging, discharging, charging, discharging. It's like there's going up and down a little bit, so it's not that clean. So therefore, typically you have a low-pass filter after this. Low-pass filter will smooth your signal. So once put this one into the low-pass filter, now you're going to get clean signal. So that's how you recover your message using this envelope detector. So this is the simplest receiver. Very simple, right? So that's the main advantage of using this envelope detector. And in order to use this simple receiver, earlier we added DC and make it always positive, right? That's the whole story of amplitude modulation we talked about. So for the amplitude modulation we just mentioned, what is the good thing and what is the problem? So good thing is the simple receiver. As we mentioned earlier, envelope detection, that's going to be the simplest one, right? So that's the advantage we have. What is the disadvantage? Main disadvantage comes from a complete waste of your energy. Why is that? Because your pure carrier contains a lot of energy, right? Depending on your modulation factor, sometimes 90%, most of your energy goes to the carrier, pure carrier, right? So your sideband only carries like 10% of your energy. So your energy transmit power is completely waste. So that's a big, big problem, and that's a big disadvantage. Okay? So that's it. That's for this amplitude modulation. So because of this problem, disadvantage, right? Because of this problem of wasting a lot of power, now the people think about another way of modulation, amplitude modulation, because this amplitude modulation is so bad, right? You're wasting a lot of energy. So this is not really good. So that's why people think about another type of amplitude modulation, and that's DSB-SC, double sideband with suppressed carrier. That's what we're going to talk about, okay, at the next topic. And even further, people thought about the single sideband. We'll talk about this one probably in 2 weeks from now, and also another one, okay? But remember that what is the advantage and disadvantage of the modulation we just mentioned, okay? What is so special about this particular modulation we talked about? You are adding DC, right? Why do we add DC? Because we want to use this one. And now, what's the problem? This is the problem. This is the problem, right? So you need to be very clear about advantage and disadvantage of this modulation. So because of this disadvantage, because of that, because this is so bad, now we want to move on to this particular modulation, DSB-SC. Okay? Why do we call this a DSB-SC? Double sideband basically means that you have both sides. Okay? Going back to our previous figure, for example, like this. This is called a double sideband. Why? Because you have like a mirror, right? Left and right exactly symmetric. Okay, maybe one question. We always, when we look at the frequency domain of our signal, we always draw like left side and right side same. We always do like that, right? We always make a symmetric in the frequency domain. Why is that? Does anyone have idea why? Why not left side this way, right side another way? Why do we always make our frequency response symmetric? Because when you go back to our second week, when we review the Fourier transform, I think I didn't talk about very detailed, but one of the Fourier transform property is that if your this is the frequency domain, right? If the time domain signal is real, meaning there's no imaginary, this is not complex, right? We are talking about the real signal. Because in time domain, there's no complex signal, right? We are not talking about complex. It's not, there's no imaginary, it's a real signal. If you look at the real signal, it's always symmetric. That's the property in time and frequency domain. So in one domain, in time domain, real, in frequency domain, symmetric, always. Okay? If you look at the frequency domain, and then left side, right side is different, in that case, your time domain signal must be complex. There must be imaginary number there. Okay? If the time domain signal is real, then it's always symmetric in the frequency domain. That's why we are always looking at the real signal. We never talk about imaginary, right? That's why we always draw like left and right like a mirror. Same image. Symmetric all the time. Okay? That's the reason. But anyway, we call this as a double sideband because you see that this one shows up double, right? Left to right, it's exactly symmetric. So it's like repeated, right? Double. So that's why we call this a double sideband. Left to right, together. That's double sideband. So this is double sideband. And what does that mean? Suppressed carrier. What is a suppressed? Suppressed. Okay? Make it smaller because you press it down, right? So suppressed carrier means your carrier will be suppressed, meaning you make a carrier very small. Okay? Because you're suppressed, your carrier will be very small. Or sometimes it becomes 0. Basically, your intention is your intention to make your carrier 0. That's what you want, right? Because in the previously the amplitude modulation, we have problem of so much waste of your power into the carrier. So that's why we want to make your carrier to be small as possible. You want to make your carrier small. You want to suppress the carrier. That's why we call it this way, double sideband and with the suppressed carrier. You want to make your carrier very small by suppressing it. Okay? Let's look at some mathematics and theory. It's very simple. Okay, very simple. In this case, what is ST? ST is what you transmit over the air. And what you transmit over the air is simply, very simply, carrier times message. That's it. Very simple, right? You have your carrier. What does a carrier look like? This is a carrier, our previous carrier. AC cosine, that's our carrier. And what is MT? It's our message. So you simply multiply these two. In that case, I just write it this way, but your MT actually is still part of your amplitude, right? We didn't touch anything about this frequency of your carrier. Your carrier still is the same. The frequency is still same. The only thing is that by multiplying MT, this MT goes into here, so your amplitude now changes. So still this is amplitude modulation because you put the message into amplitude part of your carrier. Okay? But this one, what's the difference between this one and the previous amplitude modulation? We don't add any DC. Okay? Forget the DC. We are not doing anything. We just simply, very simply multiplying message with the carrier. Very simple, right? That's it. That's it for DSPSC. Okay, now in this case then, what would be the problem? Compared to the previous case, in this case, you are not adding a DC. So now the problem is, you cannot use envelope detector, right? You cannot use envelope detector. We are not trying to use envelope detector. So we'll talk about that later, but that's what it is. Okay, so now our DSP SC signal, ST looks like this. It's even simpler, right? ST looks like this in time domain. Let's take a look at the frequency domain response of this ST. That looks like this. This is our frequency domain response. We have a MT multiply cosine. So if the frequency response of our small m message becomes capital M, then this part becomes this and this. Same as before, right? We have exactly the same as before. So now we have only two. And when you take the Fourier transform of this, now remember that we have a half here, right? Because you split it into two. So you should have 1 over 2. Okay? So this is our frequency response of ST. Okay? Remember, ST is what we transmit over the air, and the frequency response of that ST looks like this. Now take a look at the example. Let's say this is MT. This is a message, MT. So our signal looks like this. This is our message. And as an example, let's say we take a Fourier transform of our message, then we get this one. Again, example, okay? Let's say we get this kind of frequency response. Now, in this so this is a time domain, and here is a frequency domain, right? On the right side is a frequency domain, left side is time domain. We have our message MT, and what we want to do is that before we transmit, we need to do modulation. And in our DSPSC modulation, simply you are multiplying carrier with the message, right? That's what he just said. CT times MT is just ST. So just multiply the carrier, then you're going to get this. You multiply carrier into here, into MT, then you're going to get this. Now what you can see here is that we sometimes have a positive value in message, sometimes have a negative. So when you multiply the carrier here, sometimes you have a cosine, and right here you become minus cosine, right? Because original message becomes minus. When you multiply the cosine, here it becomes minus cosine. So we still have a phase reversal here and here. That's what we saw in the earlier, right? Same thing happened here. So we have a phase reversal here, because original message was negative. But that's okay. In this case. So this is your ST. This is what you transmit over there. See here, you see that there's a phase reversal, right? You goes up, like goes down, up, down, up. So it should go up, but suddenly again goes down. And up, down, up, down. So here you should go down, but suddenly up again. So you see the phase reversal here. The phase is changed. When you look at this one in frequency domain, this is a frequency domain response of this one. So these two are same, just time, frequency. These two are same, just time and frequency. Right? So this is what we transmit over there in time, and that's the frequency response of ST. When you look at here, now we have no longer impulse, right? We don't have an impulse. We have no direct delta function. We just have a pure sideband. But this is a double sideband because we have both sides, left and right, both sides, right? Double sideband in left and right. So whatever energy, whatever 100% of the energy, it goes to 50%, 50%, right? So you are not wasting any energy. No waste of energy. That's the double sideband suppressed carrier. Okay. The transmission side is so simple. This is what we talk about at the transmission side. Okay. When you transmit, what you need to do is your message multiplied by the carrier. Then you create the ST like this, and then transmit. That's what you transmit, right? Very simple. But what we need to discuss is how do you detect it? Receiver, right? Receiver is a problem because in the earlier amplitude modulation, we added the DC. Why? Because we want to use envelope detector at the receiver. But in this case, we didn't add the DC. So how do you detect? We even have a phase reversal. So how do you detect at the receiver? That's the main thing in the DSB-ST. Transmission side is so simple, very simple. But at the receiver, a little bit complex. So that's what we need to know. That's the main thing in DSB-ST. So here is a detector, receiver. Okay, detector is always at the receiver. In this case, we are talking about receiver. When we use a DSB-SC modulation, we are talking about the receiver here, right? We are no longer using, we cannot use the envelope detector, as I said. What we use is we use coherent detector. Okay, now I need to ask a question. What does a coherent means?
Clear.
Huh?
Clear.
Clear?
Sounds clear.
Sounds clear? Okay, coherent, this is a very important word. You're gonna hear this many times. Okay, when you talk about wireless communication or any telecommunication or signal processing, you're gonna hear this word many times. But this is actually a little bit difficult word. I think not many people understand it. What this means, originally coherent means something is matched. That's coherent in English. When you look at the dictionary, probably that's what they mean. But in our area, coherent means your phase match, phase. That's a synchronous modulation. That's another word. But important thing is your phase is going to match. So remember, this is very important, very basic, very important word. Coherent means your phase is going to match. If you look at the two different signals, we always has a phase, right? Because we are talking about complex signal. We always has amplitude and phase. And if both signal has the same phase, that means both are coherent. Okay? Coherent means your phase term is gonna same. Phase is aligned, phase match. That's coherent. So what the coherent detection means that you are trying to match your phase and the received signal phase. You are trying to match the phase of these two signals. That's the coherent detection. Okay, let me tell you the details here. So here, this is a receiver. So you are receiving ST. What was the ST? Our transmit signal is ST. Okay? Whatever you transmit, that comes in here at the receiver. Okay? You receive the ST. Now, first thing to do is product modulator, but this is simply multiplication. Simply multiplication. Okay? Just simple. And right here, you see local oscillator, right? And what is this local oscillator? Simply, this one is same as your carrier. So this part, right? This left part is simply you are multiplying the carrier. That's what they mean. And right after that, you are going through low pass filter. Okay, that's the basic block diagram of your coherent detector. Okay, there's a little bit more detail, but this is what happened. Let me tell you what this basically means. It's very, very easy to understand. Okay? Let's say we have our original message empty. Original message at the transmitter. Now, before you transmit, you are multiplying the carrier empty time. Your transmit signal ST is message times carrier. Okay, that's what you transmit. And this one looks like message times cosine. That's what you transmit. You have AC, right? The carrier amplitude, but let me ignore the carrier amplitude because that's just constant anyway, so that doesn't matter. Maybe you can assume the AC equal to 1. Okay, that's not important. Our message multiplied by your sinusoidal carrier. So that's what you transmit over there. Now you receive this, and what you do at the receiver is that here you receive ST. Okay, maybe I'll do this. Let me do this way. Let me do it again. You have a message comes in, and you are multiplying carrier. That's what you transmit as ST. This is a transmission block. Okay, transmitter is very simple like this, right? This is transmitter. Simply multiplying carrier into your message. And this carrier is simply this one was the carrier. So this ST was empty. Let me just ignore AC. Doesn't matter. MC cosine 2 pi FCT. That's what we transmit over there. Now this ST is received by the receiver. Here's the receiver. Okay? And inside the receiver, what you do is that first thing to do is again multiply CT. And what is a CT? The same carrier. And then low pass filter. And you are recovering your message back. Here is a UT. So this is a block diagram of the whole picture. Okay, you have a transmitter, you have a receiver. At the transmitter, what you do is message times the carrier. That's what you transmit. At the receiver, what you do is you multiply the carrier again. Okay, you again multiply the carrier, and then go through the low pass filter, and you're gonna get message back. So how does this work? I mean, you are multiplying the carrier at the transmitter, so at the receiver, you should divide it, right? Because you multiplied it, you divide it. But instead, you are multiplying it again. So how does it work? Okay, let me show you how this works. Right here. All these things, you need to be able to do it. Okay? This is very simple. So let's see that this ST is MT. MT times cosine 2 pi FCT. That's our ST. And let's take a look at the VT right here, right here. What happened is that right here, ST looks like this, right? Right here, ST is simply MT times cosine, MT times CT. Now, right here at the receiver, you are multiplying CT again. So right here, your VT now is MT times cosine 2 pi FCT square, right? Yeah. In VT, right? You are multiplying cosine again, so you square. Okay. When you remember the high school mathematics, you look at a lot of trigonometric identities. Trigonometric identity. And one of them is cosine square x equal to 1 half 1 plus no, cosine 2x. Is it right? Is it right or not? I don't remember exactly. Is it? Do we have half or not? Something like this, right? There's a trigonometric identity when you remember the high school mathematics, right? So we have this kind of thing. So using this identity, what we can write it is that we are changing this one into we are trying to change into this way. Okay? So cosine square becomes half of 1 plus cosine 2 times this one, right? Like 2x. When you take a look at here, this is a 2 times 2 phi FCT. So this one is actually same as 2 pi 2 FCT. What that means is original carrier frequency is FC. So now you are multiplying 2 times in there. So it's basically same as 2 times of frequency. 2 times over carrier frequency. So that's what they mean. Okay? This one actually is two different terms, right? We have 1 plus something. So let me separate them. So we have half here, half MT, plus half of the MT cosine 2 pi 2FCT. So that's what happened eventually. This is a VT. Still we are here, VT, right? We have this one. So we have 2 different terms. Now, when you look at this first term, we already have MT, our original message back. Okay? So this is what we want, because we want to recover original message MT, right? And in this term, we already have our original message. That's good. But now, one small problem is that we have also the second term. And this second term is empty times 2 times of your carrier frequency. Okay? Because of this 2-second term, what we want to do is we want to go through the low-pass filter. And your low-pass filter will remove this. Because this is a high-frequency component. Remember that this is a 2FC. 2FC is a very high frequency, right? Because it's a very high 2FC. So when you go through a low-pass filter, now the second term will be gone. And we are going to only have first message, first term. So therefore, when you do whole thing like this, now we can recover the message empty perfectly. Maybe you see that this is a half, constant value, half. This is not a problem, right? Yeah, when you have a half or some constant, that's not a problem. Okay, we can always multiply the amplitude, amplification. So that's not a problem. The main thing is that we recover this empty perfectly. And that's the coherent receiver or coherent detector. Simply speaking, that's what happened. Now, let's take a look at this one in frequency domain. Okay? Whenever you see everything here, you always have to look at the time domain. And also, you have to look at all the things from the frequency domain also, right? You need to understand exactly what happened in the frequency. So let's take a look at frequency. Now, original MT has some frequency response. Let's make it as a triangle. Here's a 0, because we have a message in baseband, we have a 0 here. Let's say this is our frequency response of your original message, MF. Okay? Based on this MF, your frequency response of your own message, now when you multiply the cosine carrier here, you are going to get ST. So this is ST. What's the frequency response of this ST? ST is doing modulation. So ST, original message right here is in the baseband right here. But this original message right here now becomes passiband signal like this, right? Like that. So here's FC minus FC. So now we have this one. That's the frequency response of your ST, right? Right? So this is your frequency response of your transmit signal ST. Now, based on this ST, so when you look at this one, right, what you can find out is that by multiplying cosine, when you multiply cosine in time domain, what happened in the frequency domain? Your original signal is moving on the left and right, moving into the FC frequency. So originally it was here at the 0. By multiplying cosine, this one now becomes half and half in the left and right, and the center frequency now becomes FC and minus FC. That's what happened in the cosine. Okay? Now at the receiver here in the VT, we are multiplying cosine here again, cosine. And we multiply cosine here again, right? So like a cosine square. But this one, ST, we have this frequency domain. So what happened? You multiply cosine again into here. This is ST, but we are multiplying cosine again into here. Then what's going to be your frequency response? So ST originally here, but you multiply cosine again. Now what happened is that this one, original this one, now moves to here and here. Again, it's separated by FC and FC. So this one comes in here, and this one goes into here. And here, original minus FC goes there and there. Like that, like that. So eventually, you're going to have this one, this one, this one. That's what happened when you multiply cosine again. Because you multiply cosine 2 times, right? You multiply 1 time, it goes into FC and minus FC. And you multiply cosine again, okay? This in FC now moves to 2FC and also becomes 0. And minus FC1 goes to 2 minus FC and 0. Okay? So here, the frequency response of 2FC looks like this, but the 0 here is a double of this, right? Because the signal here, the spectrum here, comes from this one and also comes from this one. So this one becomes double. And then this one. So this. That's the frequency response of this VT. Okay? This one. Let's take a look at if this one makes sense. What is the VT in time domain? This is the VT in time domain, right? This one. We have half MT plus half MT cosine 2 pi 2FC t. That was a time domain response, right? That was a time domain for VT. Let's take a look at the Fourier transform of this one. Then what do you get? If you take a Fourier transform of this VT in time domain, you're going to get this. Why is that? Because this one, half of MT, you take a Fourier transform, this becomes this, right? Because it's MT. So it's the same as this one. MT is this. So it becomes, it shows up at the center frequency of 0. Same here, center frequency 0. The only thing is you have a half. This is half. Why is it the other half? Here, 1/4. Here, 1/4. So it becomes half, right? Originally, everything was in here. Now, 50% of your energy goes in the middle. The other 25% goes there and there. Something like that, right? So this part, when you take a Fourier transform of this one, that goes in here. What about this? Let's take a Fourier transform of the second term. This one, you see that the center frequency is 2FC. And this is a cosine. You multiply cosine, right? So what happened? You have this spectrum and that spectrum. Because it's a cosine. You shows up left and right. Right? So eventually, when you take a VT, when you multiply cosine again, now you're going to get this spectrum in the frequency, this signal in time domain. So both are same. Just a time domain signal, frequency domain response. So this is a frequency response right here in the VT. Now what are you doing? What you want to do now is that you want to go through the low pass filter. And what does your low pass filter look like? Now the low pass filter looks like somewhere like this. Okay? So you always, when you have a filter, you have a cutoff frequency, right? Your cutoff frequency is somewhere here, and somewhere here. So once you pass this kind of low pass filter, now this one pass. This one blocked. So eventually what happened here? You only get this one. This one originally is exactly the same as this one. Okay, that's how you recover all these things. So this is a kind of block diagram of how to transmit and receive using this DSB-SC. Remember, this DSB-SC has no carrier. You are not wasting any energy, right? No waste energy. You are not wasting because we don't have any direct delta, right? But the problem is we cannot use envelope detector. Instead, we are using this kind of receiver. And this receiver we are calling as a coherent detector. Okay? And how these things work is that you are multiplying cosine and you are multiplying cosine again, make it cosine square. Why? Because cosine square is same as 1 plus 1 DC, right? DC plus cosine 2 times of x. So from this component, now we are going to get a 2 times FC. And this 2 times FC term will be eventually removed by low pass filter. So you are going to recover this back. Like this, right? You're going to recover it back. So therefore, you are multiplying it again. And then go through low pass filter. That's how you run the whole thing. So right here, VT, this is what I just said. When you write that as a mathematics, this is what happened. But when you understand these things, you know everything pretty much about this DSBSC. Okay? This is a mathematics. See, here is ST, incoming signal, and you are multiplying carrier again. This is a carrier. So ST times carrier. Okay? And then ST, original ST was MT times cosine. So now you have MT times cosine times another cosine, cosine square. So when you have a cosine square, now using this cosine times cosine equals to half of this one. Cosine times cosine becomes cosine 2 times square plus DC. And then becomes, you're going to get this back. Okay, so that is a basic fundamental thing. Okay. Now then, we have one more thing to talk about. We just said a coherent detector, right? And what was the definition of coherent? Phase match. And what is the phase? Basically, phase, this is a phase. This is a phase. We always say cosine 2 pi of c because we ignore the phase. But we actually have a phase, right? And if you make both, this is a carrier in Tx, this is a carrier in Rx. If you make both carrier have a same phase, like a 0 here, and also 0 plus 0, then it's coherent. That's what I did, right? I just used this one, right? So I made a coherent. Okay, I made a coherent already. So when you have a coherent carrier, then everything like this, and everything is perfect. You're going to recover this MT. Perfect. But now the problem is, this phase actually in random. This phase is random. That's the problem. In reality, you cannot make exact coherent because phase is random. You cannot control anything about this phase. So now that's the problem of the phase. So in order to, if you have some phase, and because of this phase does not match, if that's not coherent, now we have a little bit of problem. And this slide basically shows you some kind of non-matching for a phase.